Today we are looking into using light as a source for computing. So using actual photons, which are light particles, to run certain kinds of calculations and using quantum effects like interference to perform specific mathematical operations. This is what Q.ANT is actually proposing to do. This is a company based out of Stuttgart in Germany that is working on building photonic-based computers. Now, taking a quick step back, this is not, let's say, quantum computers as in using individual photons and doing some kind of manipulations, but it's more on a, let's say, broader scheme. So it is about creating light on a chip, guiding it through tiny waveguides on that chip, and then running calculations using those light particles, those collective light particles, a lot of photons, to run those kind of calculations. So you might argue that it's not exactly like pure quantum technology, but still I find it interesting. And if you do so too, then please stay tuned for today's video as we are talking about Q.ANT or Q.ANT GmbH. And with that, let's get right into it. Here we are on their website. It says Q.ANT up here. The future of computing runs on light. Photonic computing for fast, sustainable AI and HPC in data centers deployed at LRZ, Leibniz Rechenzentrum, and Jülich, Forschungszentrum Jülich, where I also did my PhD today. So, introducing the next generation of photonic processing, and that is, let's say, the main product here, right? We unveil the second generation of our photonic processor to power the next wave of AI and HPC. Learn what is new for NPU Gen 2, 8 giga operations per second, gigaops, sustained throughput on nonlinear functions, workloads where photonic processors structurally outperform CMOS. Native nonlinear operations, one optical element replaces 100 to 1000 transistors for the same function, and then foundation of wavelength multiplexing. I think we will talk a little bit about that later on. The basis of the next generation of optical scaling. Showing the path towards up to 30 times higher energy efficiency and 50 times faster computation, unprecedented compute density and bandwidth, and radical reductions in operational costs for data centers. Now, where does all of this higher bandwidth, faster computation, lower energy come from? Let's take a step back and think about the use of photonics in today's digital technology. So originally, I think the probably most prominent example where optics was introduced into existing digital technology was probably when there was this connection between the different continents. The Atlantic or transatlantic connection was created. So people were spinning a fiber from, let's say, the European continent all the way towards the American continent and connect those with some kind of digital connection. And why did they use a fiber for that? That's because using a fiber, you could transfer much more information than via a classical copper wire. So why is that the case? This has to do something with how the communication with light works. And also, the other important point is, if you're spinning such a long connection between two different endpoints, of course, loss plays a big role. So think about the landlines, think about today's power stations. If you have a power station somewhere, you have to actually transform the voltage to very, very high voltages in order to move this only for hundreds of kilometers. So moving, for example, in Germany, energy that is being produced by wind turbines in the north all the way to the south, where, let's say, the country crosses, for example, Austria and Switzerland, is not easily done because you need to transform the voltages up to very, very high voltages, and even there you have a lot of loss. Now think about the connection between the European continent and the American one, how long this actually is, how many kilometers are in between, and how much loss this would generate if you would transfer electrical signals. And that's where optics has a second advantage, right? So you have the higher bandwidth of communication and then also the lower loss of energy, because the photons, the light particles, they travel with much less loss than the electrons do. Now, We have seen over the last decades probably that of using this technology, that the distances at which those fibers have become interesting to apply have been getting shorter and shorter and shorter. So think about again of the fiber example that I shared with you before. Initially that was used to connect the different continents with each other, but very soon we saw that actually fiber also started playing a role in interconnecting different hubs with each other. So telecommunication hubs. Think about your national telecom provider that is using data centers to actually communicate data back and forth to have people exchange data. And now suddenly these hubs, they started to get connected also via this fiber network to increase the bandwidth. Following from that, you saw that, for example, large organizations, and that's still at the time where I went to school, that larger organizations like companies, they actually got access to the fiber internet as well. So first the large compute centers, which probably were not that large back then because cloud only started to become a thing once the fiber network was spreading a bit further, all the way to the point where today, as a private person, you can get a fiber into your living room to actually connect to that network. But that's actually not where it stops. If you're looking into data centers today, you see that even the compute units themselves, they already start to get connected right away to the fiber network. So you can see that some server systems, they might have optical connection going to the back where they can already themselves hook up to the fiber network and talk to the neighboring units via this optical connection. And again, this is not where it stops. It's moving closer and closer and closer. So the distances at which photons become the relevant communication source, they're getting much and much shorter because of this increased bandwidth and because of the higher energy efficiency. Now, with that being said, still, of course, there are losses. So photons, they can get absorbed. But comparing this to classical, let's say, copper wires or maybe even silver-plated wires, there's still much less absorption loss. So electrons transforming, let's say, their movement into heat compared to photons traveling through a fiber and getting absorbed here and there because they're not perfectly reflected. Now, what Q.ANT is then proposing here is basically just the thought forward. So instead of shrinking and shrinking and shrinking the connection, they say, okay, let's go away from electrons all the way. We will see later on that it's maybe not all the way, but let's go away from electrons for the relevant features and just rethink everything in a photonic way. And that, of course, requires a new technology stack. So now you need to build chips that can run on photons instead of electrons. And we will see a little bit more about how that actually works as we discover the technology a bit further. So here are some points on where this is going in terms of applications. And I think this is probably very much only the beginning, right? So it's an AI and HPC. That's because today, if we're looking at HPC, so high performance compute, one of the most prominent features that is being discussed in terms of energy consumption, there's a huge discussion right now in the US about energy consumption of training AI models, running inference on AI models. And here the idea is, okay, let's use these photonic technology, these photonic chips to actually run this workload to make it more efficient. And here the promise is to say 30 times more energy efficient. So that's more than a 10x improvement. That would be a disruptive change of how today's technology is working if that would actually happen, if that would be replaced on scale, and if they could actually keep up to that. So that is very interesting, and that of course makes it interesting also as a potential investment object or as a new technology to discover. Here we see what the server product looks like. So here we have everything integrated. So these native processing server, NPS, in something that looks like maybe a 3U rack type of setup that can go into a supercompute rack. And there's also more information about the products, as well as some white paper and some call to action to meet them in Chicago in 2026. Some announcements here about the alliances and partnerships that they have. So you see there's Jülich, which they mentioned before, and the Leibniz Rechenzentrum, LRZ. but there's also IMS chips, T-Systems from Deutsche Telekom, here the BMFTR, Bundesministerium für Forschung, Technologie und Raumfahrt, as well as IONOS as a cloud provider mentioned down here. Then you see also that it's mentioned in the Gartner Hype Cycle. If you're not familiar with that, Gartner is active in the space of technology consulting. They have created this idea of hype cycle where every new technology goes through different phases of, let's say, starting below the radar, nobody knows about it, all the way going up to the hype where everyone talks about it and everyone has very high hopes on this technology solving futuristic problems, to the way where then it kind of all collapses, the bubble bursts, and people say, okay, that didn't solve the things that we were expecting to, and maybe we were a bit overhyped on this, through the valley down here, like where people are realizing, okay, it's not completely useless, and then towards the point where it actually finds its applications, where it actually goes on scale, when it actually contributes, let's say, to the economy. So that's, let's say, in a couple of sentences, the Gartner Hype Cycle. Go check it out. It's well known among the people that call themselves economists, that have a background with this technology management. Definitely interesting to look at if you never heard about it. Then down here you find a little bit about press releases and news. I'm recording this in July of 2026, and you see also here there's May 2026, April 2026, so very much up to date. June 2026, where it says Quant runs generative AI on photonic hardware, so probably a first case where they can show that they're already running Gen AI tasks on their existing second hardware generation. There's more information here on LinkedIn, and I think from their CEO on LinkedIn, so you can also follow that, media coverage, and information about the team, way to subscribe to the newsletter, and then the typical information how to reach them based in Stuttgart in Germany, and contact details down here. Now, with that, let's quickly check out the products, the NPS that I was talking about before. And I don't want to go through all of this because I think it's similar to what we've seen before, but I want to scroll down a little bit further to here that I think is interesting. So here we see this rack mounted solution, right? The server. It's even a 4U. I thought it was a 3U, so it's a 4U server element that you can put into your existing rack. Here it says what network interfaces you have, what software you can actually run with that. Power consumption is only 150 watts, which I think in the world of servers and server systems is not a lot. So that shows how energy efficient everything is. It runs with Gen 4, 8 times in 8x PCIe lane. So that's the card that is sitting in there. And then what is interesting here, photonic integrated circuit is ultra-fast photonic core based on Z-cut lithium niobate on isolator LNOI. And here is, let's say, the two important things, right? Like the operating speed, so the transmission, the, let's say, data throughput side of things, and the energy efficiency, right? Scaled down or shown down here. So you see the different scaling approaches that they have. So they start, for example, if you're looking here at the operation speed in giga operations per second, 2026 is 1000. For next year, that already goes to 10,000. So a 10x scaling up. And then the year after, it's again a 10x speed up. So you see this exponential growth of the operations speed that they are forecasting here. Quickly on what operations they can run, because I think that is also very interesting in terms of the applications for that. So you see matrix multiplication, matrix vector multiplication, which is a major building block of today's machine learning type of tasks. Then you see image classification as something that is a little bit more top level. Of course, in an image classification task, like for example for this ImageNet, which is a specific classification network. Then you have multiple subtasks, which might involve matrix vector multiplications, but also other stuff like convolutional operations and many more. You also see a segmentation of an image here and other tasks as well. Now, here's some examples. I will not go through all of the details, some of the verticals that they are advertising here, right? So AI, inference and training, advanced image processing, and then physics and scientific simulations as part of this as well. And then down here, I think that is interesting about the technology itself. So the game changer in photonic computing, thin film lithium niobate on insulator. That's the material we talked about before, right? So Quant builds its photonic processors on proprietary TFLNOI platform. This material system enables the photonic integrated circuits, PICs, at the core of our NPUs. On a silicon wafer, a thin film of lithium niobate is bonded to create optical waveguides, modulators, and other functional blocks, allowing high-speed, precise control of light on a single chip. TFLNOI is the platform that makes scalable photonic computing physically possible. Quick step back. So bonding usually means that you are physically connecting this, in this case, TFLNOI waveguides, so optical connections that are guiding the light, like little glass fibers you could imagine. You are bonding that onto an existing chip, so you are putting it on top and you're connecting it, which means that you also still have some classical chip technology below there, which you also need. Because if you are running those processes, let's say you are running the vector matrix multiplication, now you have the data outcome of this. Okay, what do you do with it? You might have to store it somewhere, and the storing with light is very difficult because light is always moving at speed of light, and there's of course an absorption happening after a while, so you cannot store light forever in some kind of loop. You need to read it out and then put it somewhere, store it somewhere on the chip, and that's what probably likely happens here. PICs based on NFLNOI, little tongue twister, provide the physical foundation for scalable, efficient photonic computing, delivering unique advantages. Non-thermal crosstalk between optical components, since electrical fields, not heat, change the material properties. Ultra-fast modulation and switching speeds of few tens of gigahertz. Native nonlinearities offer more complex functions for computing, and then room temperature operation opens a wide range of application fields. Then you have some contact down here, as well as the newsletter. Now, I want to quickly wrap this up by talking also about the company a little bit, as you know, as per usual. So going on to the, let's say, quote of their CEO, "The future is now. It just booted up. Unlocking AI's true potential demands a fundamental rethink of computing itself. At Q.ANT or Q.ANT, we believe the future of AI computing runs on light." A couple of information about the company. So funded in 2018, 15 different nationalities, 70 plus people working there, and more than 110 patents. Q.ANT is a deep tech scale-up developing photonic processing solutions that compute natively with light and deliver a scalable, qualitative alternative to transistor-based systems. The analog coprocessors are optimized for complex computations and enable energy-efficient performance for next-generation AI and HPC applications. In collaboration with the Institute of Microelectronics Stuttgart, IMS chips, Q.ANT operates with its own pilot line for photonic chips based on the material system thin film lithium niobate TFLN. Q.ANT was founded by Michael Förtsch in 2018, and it's headquartered in Stuttgart, Germany. So also very interesting point that is mentioned in here, right? Especially in times where we talk a lot about sovereignty, European sovereignty versus American sovereignty and Chinese sovereignty, and everyone wants to be sovereign from each other. It plays a big role where the manufacturing facilities are, and we are seeing that now with the silicon manufacturing. So taking this onto and mapping this back onto this new technology, it's interesting to see that here in this specific case for this lithium niobate technology, the manufacturing line, which is still a pilot line, is based within Germany, within the European Union. So let's say the optical part, the waveguides that go on top of the chip, they are made here. It doesn't say much about, let's say, the classical microelectronics that are sitting below. So the CMOS kind of architecture might be that this is manufactured elsewhere, likely because there are places that are offering those services at very high quality and potentially interesting also here in that regard. Then you see some more information about the company values, quality, anticipate, novelty, and team. You see the CEO, and that's also something that is, I think, very, let's say, unique about this company compared to other companies where, let's say, the leadership team is of course mentioned somewhere. Here for Q.ANT, the CEO, Dr. Michael Förtsch, is very much in a prominent spot for the company. So his name is very much tied to the company, his face as well. So Q.ANT and him, it's kind of combined, it goes together. And I mean, you can have your own opinion on that, what you think about it, if you like it or if you don't like it, but it's interesting to see that this is happening. By the way, talking about CEOs, talking about the space of quantum technology, I do want to mention also towards the end of this video that this video is part of a series of the Hidden Quantum Champions, and we are about to launch a course that is relevant for everyone that is looking into quantum technology, especially for executive leadership that is looking into investing, mergers and acquisitions in the quantum technology field, for investors that are looking for the next investment rounds to get their tickets placed, like ABC investment rounds, IPOs, stuff like that, as well as founders and CEOs from the quantum space that are interested in seeing what is the competition out there, who is globally out in the world of quantum technology. This course is supposed to be an orientation to show who is out there, what is out there, which technologies, which companies are existing already, and which markets they are fulfilling. So if you are interested in that, make sure to check out the link down below the video. And with that, let's quickly close today's video. So here we see the advisory board mentioned as well. I think it's interesting and worth noting, and you see that here, CTO from Trumpf is in the advisory board. Trumpf, as a German company that is known in the laser space and the optical space, is also, and I think that's probably somewhere mentioned in here in the investors, here, is also invested in this company. So what does it mean? It means that they have an industry giant backing them, and of course moving towards production, of course that becomes interesting as well, right? To have this industry giant sitting in the back. There are also other well-known ones here, like IMEC, for example, in the semiconductor space, Worth Ventures as a very prominent technology investor. So looking at the investor landscape here, very high quality, but Trumpf for sure, let's say one of the very prominent ones in there, and one of the ones that add a little bit of additional weight onto this company's probably trajectory, but also onto the things that are being proposed here. So definitely an interesting observation as well. Then, I mean, you see here contributions to BMFTR, Bundesministerium für Forschung, Technologie und Raumfahrt, mentioned that before, as well as other stuff mentioned down here, networks that they are part of, like Bitkom in Germany and many others, and the links as per usual. With that, I want to close today's video. So this is not, let's say, fully quantum, right? Even though using light for computation, from my point of view, is quite quantum, but for some of you that might not be quantum enough. But I hope you anyways liked it. If so, make sure to give it a thumbs up. I'm looking forward to see you in the next one. As always, stay hydrated, and until then, bye bye.